And let's see, page 429. And number 11. Okay, rewrite the other form. Is log or real is exponential. Okay. This is number 11, page 429. We got log of base 4/3 of 3/4 is equal to -1. Now this is based upon our definition of a log in exponential form. So we have our log form, which looks like this. Log base b of q is equal to p. Now if you have it in that form, you can rewrite it in your exponential form as b to the p is equal to q. Well, it matches our log form, so the number the smaller that follows your log, that's kind of set down a little bit, will be your b. It's your base. So this is our base, and then what follows that is your q. So the 3/4 is our q, and what's on the other side is our p, which will be the -1. So then for our exponential form, we're just going to plug it into the b to the p is equal to q. So we're going to have 4/3 to the p power, which is a -1, is equal to q, which is 3/4. And that's our answer. The instructions on these is they just want you to go back and forth between the exponential form and the log form just to get practice on them.
Okay.
Number 32. And I'll go ahead and work this problem, and then I'll put right down the property. Property may look complex, but it's a very simple idea. 7 to the power of log base 7 of 3. If whatever number you have here matches your base, and it's in this form where you got 7 to the power of log base of something. So if those 7s match, then those 7s and the log cancel, and our answer is just 3. It drops out of the exponent. Now the property on that says if you have b to the power of log space or base b of q, that's going to give you q. So whenever those numbers match, then it always just drops out and gives you the whatever's over here.
Okay. Presley, can you do number 25 also? The log, log parentheses 1/1,000,000.
So 25 log base, okay, and 1/, is that 1,000,000? But my eyes are very good.
I think so. Yeah, it's 1/1,000,000.
Now, since there isn't a base here, This is by default base 10.
Base 10, okay.
And our goal is to try to rewrite this as 10 to a power. Well, the first part's easy. When you got 1 million, you can rewrite that as 10 to the 6th power. Now, the exponent will always match how many zeros you have. Now, that's really close to being in the right form.
Is it log 10 to the negative 6 or something?
Exactly. I just had to move that up on top. You move anything opposite of where it's at in a fraction, the sign of the exponent changes. Now, if these, and I'll write down the property after I do this problem, but if these numbers match, then the log and those numbers will cancel, and that'll drop out of the exponent, and your answer is just negative 6.
Okay.
Now, the property on that says, if you got log base b of b to the p power, then that just gives you p.
Okay. Are there any other properties I should be aware of, Professor, for logarithms? There's like E, ln, is that natural log, and forget what E is.
Yeah, that's
E,
natural log.
okay.
Some of these are interesting. I don't know how to work number 42. Oh, yeah, I do. Oh, that's a tricky one. I was thinking about using a property, but log of 1, if let me show you, is equal to 0. Which means log of 1, 0, 0 times 6 is 0, 42 to the 0 power is 1, and then you got natural log of 1, which is equal to 0.
Oh.
Is there any other properties for this section?
Is it just kind of manipulating exponents and using those two properties we talked about so far? Just,
exactly. You're trying to get it to look like where you can match the base. Like this is 36, you're trying to rewrite that as 36 to a power. See,
okay.
31, that'd be 36 to the 1/4 power.
Right.
And so then 36s and log would cancel, and your answer would be 1/4.
Okay.
Now sometimes it's not so easy to see how to get in the right form. Let's look at 28. That one's not jumping out at me. Let me clear this off. Number 28, we got log base 4 of 8. And I don't see how to rewrite 8 as 4 to a power. So I'm guessing on this one you want to use a different property. Now we don't know what that's equal to, so that's equal to blank. It's equal to something over here. Now if I pick a variable like x, then all of a sudden this is in log form. You have to introduce the variable. This right here would be our b. Whatever follows is our q, and then the other side of the equals is our p. And then our exponential form says b to the p is equal to q. So b is 4, p was x, and q is 8. Now this uses something called the equality of exponents. And I got a feeling that there's some way I should be able to see this. Mind you, I'll be able to see it after I do this.
But it's too cute. Can you rewrite it like that at all? Or
yes, and then 4 I'll rewrite as 2 to the 2nd power.
Okay.
Now the equality of exponents says if this is 2 to a power and this is 2 to a power, then you can cross those 2's off and you set the exponents equal to each other. So you'd have 2x is equal to 3. Divide both sides by 2, and you get x is equal to 3/2.
Okay.
If I had been able to see that to begin with. What that means we could have rewrote 8 as 4 to the 3/2 power.
Right.
And
It's
now,
not very obvious, though.
yeah, it's not very obvious. Now that I see that, it's like, okay, that's pretty clear that would give it to you, because 4 to the 1/2 is the square root of 4, which is 2.
Right.
And then 2 to the 3rd power gives you 8. So then the 4s would cancel, and you'd have 3/2. The idea of using this property is you do not have to go through all this to solve it.
Okay.
That's assuming it's easy to see.
Well, like number 27, ln to natural log 3.
If we had 27, we have natural log of e to the 3rd. Now, natural log is a special case of a log, and it's specifically when your base is e. So if I were to put the base there, it'd be e. And just like when we're working with regular logs, if these numbers match, e is just 2.7 in quite a few decimal places. Then the natural log and e are going to cancel, and our answer will be 3.
Okay. All right, I think I get the basics of logarithms now.
Okay. Let's
What
see.
about the next?
445. Number 14. Okay. Well, this goes back to some properties. Properties of logs. Our first one says if we have log of something plus log of something else, then we can rewrite that as log of the two items multiplied together. Addition becomes multiplication.
Oh.
If we have log of something minus log of something, then subtraction becomes division. And if we have typically a number in front of the log, p log m, then we can take that number that's in front of the log and put it as our power.
Multiply it by put it to the power.
Put it as a power.
Okay.
Now, I'm sorry. Go ahead.
Oh, interesting. I didn't know that. Yeah.
Now this is the product property is first one. The second one's a quotient property, and this third one's a power property. Now you can go both directions. If we start at the left side, you can use it to condense it into a single log by going to the right. Or if you start at the right side and start with a single log, you can go the other direction to expand it.
Okay.
Now in college algebra, we mainly go from left to right because we want to end up with a single log when we're solving log equations.
Now, does it change the base at all, or does it have to?
No,
You can't.
all the bases do have to be the same, and this applies no matter what your base is on your logs.
Okay.
Now going the other direction, where you go from a single log and you expand it into multiple logs, that would be something that would be beneficial in a calculus course.
Okay.
Okay, so let me clear this off. And number 14. And 14. Got log base 1/2. 4 cube root of x squared. Over y square root of z. Pretty much throughout every section dealing with log, you never want radicals. So I'm going to rewrite these. This will be 4, and this will be x to the 2/3 power. And this will be y z to the 1/2 power. Now when you're trying to figure out how to, we're going to look at expanding these. Expand the given log and simplify. Assume when necessary that all quantities represent positive real numbers. So we want to expand these into separate logs. You have to ask yourself, what's the main thing happening in the problem besides log?
So quotient, I guess?
Quotient, yeah, because we got the top part divided by the bottom part. Well, from our properties, division becomes subtraction. So this will be log base 1/2 of 4x to the 2/3 minus log base 1/2 of y z to the 1/2.
Professor, could you rewrite that as, instead of quotient, could you do it through the product property if you did like y to the -1 power and z to the -1/2 power? Could you bring it up into the numerator? Okay.
Yeah,
it makes more sense. It's already set up as quotient.
Now looking at your first parentheses, you again ask yourself what's the main thing that's happening. You got multiplication and you got a power. But and when I say the main thing, I'm talking about that would involve everything in there. And that'd be the product. Because we've got this times this. If I said it was the power, well, the 4 isn't being raised to the 2/3 power.
Right.
So the multiplication gets rewritten as addition. Minus, and then I'm going to put a bracket here. As you rewrite this log, you want to make sure that this minus, this negative, affects everything to the right of it.
Okay.
Well, same thing here. We got multiplication and we got a power. The power isn't being applied to everything, though. It's just being applied to the z. So the main thing that's happening is multiplication. So this will be log base 1/2 of y plus log base 1/2 of y to the 1/2.
Z to the 1/2, I think.
Yeah, it is z, isn't it? Let's try it again. Z to the 1/2.
Does that cancel then? If it's base to some x to the 1/2, does that cancel out, or is that not?
No, there are actually different factors that gets applied.
Oh, okay. If it was 1/2 or base 1/2 of 1/2 to the z, then it would just be z, right? Then it'd be.
That's correct. Yes.
Okay.
Now, if we got numbers, we try to see if we can simplify this. So the question is whether we can rewrite 4 as 1/2 to a power. Well, it seems like we should be able to. If I come up here, 4 is like 4 to the 1st power. To start off with, I could rewrite 4 as 2 squared. Well, that's a little bit closer maybe. But if I think about going the other direction, if I raise 1/2 to what power would it give me 2?
-1.
-1. So this right here is equivalent to 2. So this becomes 1/2 to the -1 raised to the 2nd power.
Okay.
That one's kind of a complex one. So that's 1/2 to the -2 power. Okay. Now our goal is to simplify the numbers, but also to get the variables by themselves if we can. And here, the only thing left is a power, and we said we can take the power and we put it out in front of the log. Like that. Remember this negative that's out in front, that's going to flip the sign of everything inside.
Right.
So this becomes a minus log base 1/2 of y. Now here I'm going to take that 1/2 and put it out in front of my log, and also flip the sign.
All right.
And then the last thing, since these 1/2s match, the log and the 1/2's going to cancel. And we got -2 plus 2/3 log base 1/2 of x minus log base 1/2 of y minus 1/2 log base 1/2 of z. And that's our answer.
Okay.
Let's see, number 21. Okay, this is going the other direction. We want to condense these into a single log. So log x minus 1/3 log z plus 1/2 log y. The only time you can use properties 1 and 2 is when you have nothing in front of the log. It simply has to be log of something plus log of something, or log of something minus log of something.
Okay.
So if you have anything in front of it, you can't apply it directly. And I see that I got some numbers in front of these logs. So first thing I'll do is I'll get rid of those numbers.
So the p log m equals log m to the p?
Right. So these both become our powers.
Professor, could you do when you do log x minus log z to the 1/3, could you also do log x plus log z to the negative 1/3, or does
Yes, you
that
could.
You could?
That'd be fine.
Okay.
You just have to make sure at the very end that if you have any negative exponents, you typically want to get rid of those.
Okay.
Now, going the other direction, we asked what was the main thing that's happening. Going this direction, we basically look, we have follow order operations. So order operations typically tells us to do addition, subtraction from left to right. So I'll do these first, 2. Now subtraction becomes division. So this becomes log of x over z to the 1/3. And then that other log carries down. Now we have just one thing left, log of something plus log of something, and addition becomes multiplication. So this will be log x y to the 1/2 over z to the 1/3. Now, depending upon the book, they may have you put it back in the radical form. They may have you leave in this form. I haven't checked this, but that would be your answer.
Okay.
Are those making sense?
Yeah, yeah.
Okay. Let's see, page 456. Number 14. Okay, this is an exponential equation. Now, solving an exponential equation, now our first step is to get the part with the variable in the exponent by itself. Nothing in front of it, nothing after it. You just have whatever has the variable in the exponent by itself on one side of the equation. And we'll see what I mean with the example in that. Step 2, take natural log of both sides. Step 3, use properties of logs to get the variable out of the exponent. And step 4, we want to solve for x or whatever variable we have. So let's apply this to the one we're in the book. Let me clear this off. Let's see, this is page 456, number 14?
Yes.
Okay. Number 14, what's that say? E to the negative 5730k is equal to 1/2. Okay, so let's follow our steps. Step 1, get to par with the variable and the exponent by itself. Well, it's by itself. There's nothing in front of it. There's nothing after it. We just got e to a power.
Okay.
Step 2, take natural log of both sides. So we're going to have natural log e to the negative 5730k is equal to natural log of 1/2. Now remember, natural log has base e. So in step 3, where it says use properties of logs to get the variable out of the exponent, well, remember when these numbers match, they cancel. So we got negative 5730k is equal to natural log of 1/2. And then step 4, I said solve for x, but in this case it's a k.
Divide by 5730.
Exactly. Divide both sides by negative 5,730. And I won't actually plug that in the calculator, but that would give you your answer.
Okay. Professor, for our final exam, are we allowed to use calculators?
I'll double check on that, but I'm pretty sure you are.
Okay. It's okay to use like calculators online, I guess, or should I get like I guess my iPhone can be used as a scientific calculator.
Now that I bet they won't let you use.
Okay. All right.
It is a proctored final, so
right.
And so you go in, and I'm assuming that the reason why is there's apps on especially on the iPhone that you point it at your problem and it actually solve it for you.
Oh man.
Yeah, it's unreal. some of the websites that are available on these.
That's cool. I mean, it's not honest, but I mean, it's pretty cool. Pretty neat.
Yeah, the technology is actually really cool.
I'll be taking. I mean, I live in Korea, so I'll be taking through ProctorU, I guess, which is like a online proctoring service. I have my little MacBook has a video camera, so I'll be using.
Okay, yeah, I've used ProctorU before. Yeah, they have you. I'm sorry, go ahead.
Oh, are they? I was reading kind of mixed, lukewarm reviews online.
Really?
Are they fairly? Are they? I mean, I don't know. I think perhaps some of these students just, aren't prepared for exams and then kind of take out their frustration on, like a third party, which isn't particularly, unbiased.
Yeah, they have you they'll have you point your webcam around the room and make sure there's nobody sitting next to you, and then they watch your screen while you're doing it, so you don't go to some online website that will solve the problem for you. And
all right, that is really neat. The only other person here is my wife, and she's not too good at math, so shouldn't be a problem. All right.
Let's see. Is there any other ones you wanted to see out of that?
I think I get it. Just you isolate the. I'm a little bit. Can you elaborate on E and ln, or E and ln is natural log, right? And is E the base of that?
E is the base of it, correct. Whenever you see ln, that's natural log, and it's always base E, that 2.7, quite a few decimal places.
So, like, what is it? I mean, what is...
Oh, it just, it really affects how fast your graph grows. So an E represents the natural growth. Like if you had bacteria and so forth, and they kept multiplying, that would be one example. Population growth uses E a lot.
So this is like exponential growth then, right?
Exponential growth, right. And it's kind of, I think of it as the ideal. growth, where you can have other exponential growth that's not based upon e. You can have any number there actually. E is used a lot in business though.
Okay. I was watching your video the other night, Professor, about the deficit or the debt. It's national debt. It's pretty
Oh, right.
interesting. Interesting video. I had no idea that. I mean, it just. I'm still a little confused as to like how it got to the point of exponential rate. Like, was it just heavy borrowing, I guess, from like depleting?
Just when you keep borrowing money and so forth, and you just keep, as it gets worse and worse. At first, the interest is very little you're paying, but then as the amount that you owe gets larger, then all of a sudden that interest starts growing exponentially.
Okay.
So
Okay.
it's a very nice thing if it's your retirement. Because that's what used to be. Of course, it isn't as good as it used to be, but used to be when you started investing and so forth, you never didn't put very much in. It was just growing slightly, and then over here at age like 60, 65, it would be flying out of sight. So you'd have this huge chunk of money when you got ready to retire.
Well,
I think, this is like based upon age 20, where you're started investing. My wife, I think, started us investing at age 35, maybe. And you can get a little bit of money at the end, but you don't get that ramp up where it's flying out of sight. You have to have a certain time period to pass before it does that.
Interesting. My wife is Korean. I'm American, and they have this kind of neat system to promote. A lot of international marriages are kind of like maybe like from third world countries or like developing countries marrying Koreans. So the banks have these savings programs where you can invest like $200. I think it's like $200 per month, $200 to $400 per month, but it's at a 4.5% rate. So it's like really good interest, but it's like limited. But I think towards the end it gets like it's like a 2-year or 3-year deal. Towards the end, the interest rate is pretty decent.
Yeah, that's excellent.
Yeah.
I wish I could get that kind of percent down at the bank.
Yeah. I heard it in America here. It's weird. It's like the interest rate doesn't even cover inflation. I mean, inflation's like 1.5% a year, and savings accounts are like from what I read, is like 0.5. So I mean, you're losing money by. I mean, it's like negative, right? Is that correct?
That's correct.
Jesus, it's bizarre.
Yeah, somebody's winning.
Jeez. All right, Professor. Page 482. Number 952. And logarithmic functions, essentially, these are to like the inverse of exponential functions, kind of.
Exactly.
Okay, that's cool.
Okay, so number. Oops, I didn't go up for nothing. Number 9. It says, how much money needs to be invested now to obtain 5,000 in 10 years if the interest rate in the CD is 2.25% compounded monthly? Round your answer to the nearest cent. Now, there's two types of formulas. If it says compounded continuously, it's the A is equal to P e to the RT power. If it does not say continuous, then it's A is equal to P times 1 plus R over N to the NT power. So that tells you which formula to use. Like this one on number 8 says compounded continuously, you'd use that PERT formula. Now it says how much money needs to be invested. Well, what they're asking there is, so when I get back there, is what is P? So we don't know what P is. How much money needs to be invested now to obtain 5,000 in 10 years? So 5,000 is going to be our ending amount. So that'll be our A. A is your ending amount.
Okay.
And then R, it said was 2.25%, and we want that in decimal form. So it'll be 0.0225. Over N, and N is the number of times compounded per year.
12?
Monthly, yes, 12. And then up here I'll have N, which is 12. And I'll put a little X to indicate multiplication. And T is the number of years.
5 years, or 10 years.
10 years?
See, 10 years.
Yeah. So then, we want to do a little bit of solving first. We got 1 plus 0.0225 over 12. And you should go ahead and do this part in your head. 12 times 10 is 120. Now, it depends on what kind of calculator you have, but this right here is just a number. Starting at the beginning parentheses, 1 plus 0.0225 over 12 to the 120th power. That's what I can do. And if you got a like a scientific calculator, you're probably best to do it but piece by piece. I'm going to do it on a TA3, TA4, and in that case I can just plug it in all at once. So if I do a beginning parentheses, 1 plus 0.0225 divided by 12, closing parentheses, caret 120, and then enter. And that gives us 1.25205 8912, and you typically do not want to do any rounding till the very end. So then I'll take, to get P by itself, I'll divide 5,000 by that number. So then, if I do 5,000 divided by previous answer, I did second negative to bring previous answer up, then I get 3,993.42. And that's our answer.
All right. Okay.
You got that all written down?
Yeah, yeah.
Okay.
I get it.
Now number 15.
Yeah, half-life question.
It tells us up here that our basic formula is A of t is equal to A naught times e to the kt Now the this right here is your end amount. That's what that represents.
Mm-hmm.
And this A naught represents your beginning amount. And the T here represents time, of course. But it represents it, actually I shouldn't say years, because it doesn't have to be years. It's whatever makes sense for whatever you're dealing with.
Okay.
Okay. Now they tell us for number 15, phosphorus 32 used in agricultural, initial amount is 2 milligrams. Well, the beginning amount we said was A naught.
Right.
So they're telling us that's 2. Half-life of 5.27 years.
Oh, 15. Half-life 14 days.
Oh, half-life 14 days. And the eyes are in a run. Okay, so t is equal to 14. And what was that, half-life?
Yes.
Okay. And that's for our half-life. And then the problem up here says find the decay constant k. Round your answer to 4 decimal places. And that's kind of assumed you have to find k on these problems.
Mhm.
Now, half-life. If it starts with 2 milligrams, half of that's going to be 1. So our
Right.
ending amount is going to be 1. Our beginning amount was 2.
Oh.
That's why you have to read it carefully. If it says half-life or quarter life or whatever, then you
Right.
have to
Okay.
apply it appropriately.
So
K,
K to the
yeah,
14.
and then 14, exactly. So then I got, this is an exponential equation. Let me rewrite it first. I have that. And our exponential equation, step 1, get the part of the variable and the exponent by itself. Well, it's not quite by itself. It's got a 2 in front of it. So we're going to divide both sides by 2. So we got 1/2 is equal to e to the 14k power. Step 2, take natural log of both sides. So we're going to have natural log of 1/2 is equal to natural log of e to the 14k. Step 3, use properties laws to get the variable out of the exponent. Well, remember, if you have natural log, that's base e. And
Right.
if these numbers match, they cancel. So then that gives us natural log of 1/2 is equal to 14k. And to get k by itself, I divide both sides by 14. So we got natural log of 1/2 divided by 14.
Okay.
Now we're going to round up to 4 decimal places. So I do natural log of 1/2 divided by 14. In 4 decimal places, we'll have negative 0.0495 is equal to k. I think that's the first thing they're asking for. Find the decay constant. Now it says find a function which gives the amount of isotope A which remains after time t. Keep the units of A and t the same as the given data. What that means is we're now going to plug that k back into our formula. So A of t is going to equal to, now our beginning amount. Beginning amount they told us was 2. And then E and K we just said was negative 0.0495 times T.
Okay.
So that's our function. And determine how long it takes for 90% of the material to decay. And they give you a hint. Ran your answer to 2 decimal point. Hint, if 90% of the material decays, how much is left? Because
So,
remember, oh, go ahead.
oh, so 10% would be.
Right, so I take 10% of the initial amount, so 10% times 2. So then, 10% of 2 would give us, I hate decimals, what was that, 0.2?
Yes.
Equals 2 e to the negative 0.0495t. And this is actually another exponential equation. Exponential equation is when you got a variable up in the exponent.
Mhm.
So, step 1, get the part of the variable and the exponent by itself.
5 by 2.
Divide by 2.
So 0.2 is 1 over 5, right? So you can just do 1 over 10, I guess, right?
You could, or
Basically.
you could leave it as 0.1. Either way is fine.
Uh,
Because eventually you're just going to end up plugging in your calculator anyway, so that's up to you.
Right.
Um, let's see, e to the negative 0.0495t. Now our second step.
It's natural log.
Take natural log of both sides. So we've got natural log of 0.1 is equal to natural log of e to the negative 0.0495t. And remember, natural log and e cancel each other out. So that gives us negative 0.0495t. And then divide both sides by negative 0.0495. And that'll give you your answer. I won't plug it in the calculator, but...
All right.
Does that make sense?
Yeah, totally.
Let's see, number 22.
Yes, I might actually have to run. I got to start preparing for work.
Okay, well, I'll go ahead and finish 22, and then I'll put in the recording.
So
you
that'd
can
be
watch
great.
It later. So.
Oh, yeah, thank you.
Have a good night. Or morning over there.
All right, take care. See you next week, Professor.
See ya. Okay, number 22. Let's see. Diameter D of a tumor in millimeters, T days after it's detected, is given by this. So D of T is equal to 15 e to the 0.0277 t. And it says, what was the diameter of the tumor when it was originally detected? Now, when I say originally detected, they're talking about time is equal to 0. Let me think if that's a true statement. In millimeters after it's detected. Okay, yeah, t days after it's detected. Because t does not represent when you actually got the tumor. It's just when it was detected. So yeah, t is equal to 0 would be what we'd want to plug in. So I got 15 e to the 0.0277 times 0, which gives us 15 e. 0 times anything is 0. And e to the 0, anything to the 0 power is 1. So this would give us 15. So that would be our answer for part A. Now part B. It says, how long till the diameter of the tumor doubles? Okay, so originally it's 15, and doubling the diameter would be 30. So they're telling us to plug 30 in for the diameter, and then I got 15 e to the 0.0277 t. Now this is again an exponential equation, so our first step is to get part of the variable in the exponent by itself. Can't have any numbers in front of it or after it. So we'll divide both sides by 15. So we got 30 divided by 15 equals e to the 0.0277 t. 30 divided by 15 is 2. Now our second step in solving the exponential equation is to take natural log of both sides. So we got natural log of 2 is equal to natural log of e to the 0.0277 t. Now remember, natural log and e cancel each other, so that's 0.0277 t. And then we'll divide both sides by 0.0277. So we got natural log of 2 is divided by 0.0277, and that's going to give us our time. I won't actually plug that into the calculator, but that'll give you how long will it take before it doubles.